Okay, welcome back. Let's do some more separation of variables examples. I'm going to be working off of the extra practice for 5.3 that's, I think it should be available in your notes packet. It's definitely, linked on the calendar page for separation of variables. It's the one that's going to start off, I had it. Okay, it starts off with dy dx equals negative x over y, find the general solution. Okay. All right, so let's get everything set up. And all right, now I can see where I'm working, and dy dx equals negative x divided by y. Okay, so y dy equals negative x dx. I'm going to anti-differentiate both sides. I think this one was in the examples. Yeah, it definitely was. Okay, so I anti-differentiate both sides. Now I'm going to start to solve at y because there's no initial condition given. I'm just finding the general solution. So okay, remember, I don't do algebra with plus c. I'm just going to multiply 2c, and that's just going to be some new arbitrary constant. And then I'm going to take the square root of both sides of this equation, and I'm going to have to remember the plus minus. Now, if we had a particular solution, we'd be able to determine which it was, the plus or the minus, but that'll be all. Okay. This is the equation of slopes for a circle. It's also the equation of part of a circle. Okay. But I think that's all I'm going to say about that. The second one is dy dx is x to the 4 minus 1 divided by y squared. So y to the 2 dy equals x to the 4 minus 1 dx. Anti-differentiate both sides. I'll get 1/3 y to the 3rd equals 1/5 x to the 5th minus x plus c. Now I'll start to solve at y, and I'll start by multiplying by 3. And that's still going to be c. Okay, I thought I'd worked this problem before. I'm sure I have worked this problem at some point in my life. I thought maybe I'd worked it on the previous example video and I didn't want to do it twice, but this is a different one. So y is the cubed root of 3/5 x to the 5 minus 3x plus c. Okay, with the cube root going over all of that stuff. Okay, and then the initial condition that they gave me was x is 0 and y is 3. So 3 is, oh, I worked this one in class for one of my classes. I remember now. Okay, it was like, this problem seems very familiar. The cubed root of 3/5 of 0 to the 5th minus 3 zeros plus c. Well, we know that 3 is the cubed root of 27. So I'm going to say, oh, and in the previous example video, I did I did this step in red, and I am committed to continuing to do that. I just forgot this time. So I'm just going to say c equals 27. And as a result, my solution is y equals the cubed root of 3/5 x to the 5 minus 3x plus 27. And, so this was my work in finding the value of c by plugging in my initial condition. Okay, number 3 is dy dx equals x times y with the initial condition 0 and 11. All right. Okay, so I'm going to divide both sides by y. 1 over y dy equals x dx. I'm going to anti-differentiate both sides. And I'm going to get natural log of the absolute value of y equals 1/2 x squared plus c. Okay, I'm going to get rid of the natural log by taking e to both sides power. But I know that I don't have to write plus c in the exponent. This is really this multiplied by e to the c, and e to the c is some other arbitrary constant. So I'm going to put that there, and I'm going to drop the absolute values, which induces a plus or minus on the other side. And now I'm going to use my initial condition. So it said when x is 0, y is 11. So 11 is going to be a positive number, so I'm going to choose positive c e to the 0. So that means c is 11. And my solution is y equals 11, positive 11, e to the 1/2 x squared. Number 4, dy dx is equal to x times, wait, no. Oh, whoops. Okay, I just did number 4. Number 3 was doing this with 0 and -7 as the initial condition. I missed that. And so what I'm going to do instead is, what am I going to do instead? I'm going to just kind of go off to the side here and say, okay, so this was 3 and 4. How about that? And so this is for number 4. For number 3, I'll switch up the color this time, and I'll do in blue. So for number 3, yeah, it's still in the shot, I'm going to say y is equal to -7. -7 equals a negative number, so I'm going to say negative c e to the, again, 0. Okay. So in this case, all right, I need to use the negative, but c is 7. Or if you said it was positive, you know, you get c equals -7, who cares, right? You're going to end up with your final solution being y equals -7 e to the 1/2 x squared. All right, I already did number 4, so this is going to be number 5. All right, and e to the y plus x. I think there was one similar to this on the homework, but it's okay, I'll do it again, because I think this comes back again at some point in near future. So I'm going to say that this is e to the y times e to the x. I'm going to divide both sides by e to the y. So I'll have 1 over e to the y dy equals e to the x dx. But we don't like anti-differentiating fractions, so I'm going to rewrite this as a negative power of e. Okay. And then I'm going to anti-differentiate. I'm going to get e to the -y divided by -1 to prepare for the chain rule there. That's equal to antiderivative for e to the x is e to the x plus e. Now I'm going to start trying to solve at this y, so I'm going to multiply by -1. Okay, minus c is just plus a new c. Get at that y by taking the natural log of both sides of the equation. And maybe I'll write that as c minus e to the x. I don't know, just make it a little different, mix it up some. But we know that, you know, -2 plus 3 is the same as 3 minus 2. So it's the same thing. Now I'm going to use my initial condition they gave me. That's going to be when x is 1, y is -1. Okay, so -1 equals the natural log of c minus e to the first. Well, this one could end up being a little weird. What I'm going to do is I'm going to take e to both sides power to get rid of that natural log, right? And so I'm going to have e to the -1 equals c minus e. So it looks to me that c is, I'm going to add that e over there, e plus 1 over e. I'm sure there's a way that we could simplify that more, but we don't need to. So I'm going to say y equals the natural log of e plus 1 over e minus e to the x. And again, although this looks like something you want to be able to apply a log property to, there's nothing you can do to that. Nothing else you can do. Because we can't split a log over addition, there's no log property for that. Okay. Then, let's see, the next one, sine of 4x. It doesn't even have a y in it. So I'm just going to say, what's that? It's number 6. Sine of 4x goes to the point pi over 4 is 7/4. Okay, well, that means that when I anti-differentiate, I'm just going to get y by anti-differentiating sine of 4x with respect to x. And so an antiderivative for sine is negative cosine, but I know that that 4x is going to cause me a little bit of issue, right? Because when I take the derivative of this, I'm going to have a 4 come out for the chain rule. So I need to prepare for that by dividing by 4. Okay. And then I'll use my initial condition. X is pi over 4, y is 7/4. So it's negative 1/4 of cosine of, when I plug in pi over 4, I'll get pi there, plus c. All right, and now at pi, okay, the cosine is the x value, and that's going to be negative 1. So 1/4 times negative 1 is positive 1/4 plus c. C is looking like 6 divided by 4. And so my particular solution is negative 1/4 cosine of 4x plus 6/4. This is one that kind of looks not separable, but it's going to become separable when we go and factor some stuff out. All right, x squared y squared minus 4y squared. Okay. And while this thing could be factored further, right, I could make that x plus 2, x minus 2. I don't want to because it's not going to help me anti-differentiate at all. So I'm going to need to just start by separating variables. Anti-differentiating. Okay. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Same story over here. Don't forget to plus c. All right, start getting out the y. Okay, y to the negative 1 equals 1 over y, meaning that y is going to equal 1 over negative 1/3 x to the third plus 4x plus c. Okay, now I'm ready to use my initial condition. And that's when x is 3, y is 1/5. Okay, negative 1/3 of 3 to the third is going to be negative 1/3 of 27, negative 9. Plus 4 times 3 is 12, plus c. So really I just need a 5 in that denominator, so I've got 3 plus c equals 5, that means c equals 2, right? So I've got y equaling 1 over negative 1/3 x to the third plus 4x plus 2. All right. For 8 dy dx equals y minus 2 over x plus 1. So this one's going to end up being a little weird, I think, because, right, it's going to have logs on both sides. Okay, so it'll be all right, though. 1 over y minus 2 dy equals 1 over x plus 1 dx. And, well, this will be natural log of the absolute value of y minus 2. And if you're unsure about like the impact of the minus 2 on this antiderivative situation, check it by taking the derivative. You know, you're going to want to ignore the absolute values for now. But pretty much what's going to happen is I'm going to get 1 over y minus 2 times the derivative of y minus 2 with respect to y, and that's just going to be 1. So it'll work. That's a valid antiderivative. And so that's going to equal log of the absolute value of x plus 1 plus c. And then I will... Okay, I will take e to both sides power, and I'll have the absolute value of y minus 2 equals c e to the natural log of the absolute value of x plus 1. Okay, we know what that is. Okay, but you don't have to simplify that if you don't want. Okay, maybe I won't. Maybe I'll just hold on to it for now, and I'll see maybe later if I feel like doing that. So I'm going to get y minus 2 equals plus or minus c e to the natural log of the absolute value of x plus 1, which is just going to be the absolute value of x plus 1. But I'm going to add 2 to both sides, and I'm going to get 2 plus or minus c e to the natural log of x plus 1. And if you're not sure, if you're ever unsure, you can just leave it like this and just keep carrying it with you as far as you need to go. The initial condition I've got is x is 1, y is negative 4. So negative 4 equals 2 minus 6, right? So I know that it needs to be a minus here, and I'm going to put c e to the natural log of the absolute value of x is 1, so the log of 2. Okay, that's 2. Okay, so negative 4 equals 2 minus 2c. And I decided I'm using the minus. So I'm going to subtract 2, and I'm going to get negative 6 equals negative 2c. That tells me that c needs to equal 3. And so we could say y equals 2 minus 3 times e to the natural log of the absolute value of x plus 1. That's cool. Or we could say y equals 2 minus 3 absolute values of x plus 1. I feel like there might be something I'm not considering happening there, but at this level in this class, these are going to be equivalent. I feel like there might be like some sort of domain restriction to the solution that I'm not thinking of, but that's really not something they ask about in AP Calc. The domain of a solution to a differential equation. That's just not part of it. Okay, let's see. Number 9. Okay, I don't think that should take up too much room. I took up almost that whole sheet for that one problem. I think I can get number 9 in pretty quick. Okay. dy dx equals 1 minus y. Okay, so I'm going to divide both sides by 1 minus y, right? Just look at it like that, Okay, I'm going to anti-differentiate both sides, and okay, this is going to be close to the log of the absolute value of 1 minus y, but I know when I take the derivative, I'm going to get 1 over 1 minus y times the derivative of 1 minus y with respect to y is times negative 1. So I'd be off by a factor of negative 1 there, so I'm just going to prepare for that by putting a negative there. Antiderivative of 1 with respect to x is just x, and I'll put the plus c over here. All right, and then after that, I'm going to, what am I going to do? I think I'm going to, deal with the negativity first. So negative x plus c. Take e to both sides power. Uh-oh, running out of room. So I'm going to say 1 minus y equals plus or minus c e to the negative x, and I'm going to jump back up over here and say I'm going to subtract 1 and then multiply by negative 1, so it's going to be 1 plus or minus c e to the negative x. Kind of did multiple algebra steps there, but negative 1, positive, yeah. Plus, minus, minus, plus, same thing. Okay, now my job is to use the initial condition, which was 0 and 100. So y equals 100 when x is equal to 0. So 1 plus c times, not 0, e to the 0. Okay. And that means that c equals 99. Is that, yep, still in the shot. So my conclusion, my particular solution is 1 plus 99 e to the negative x. Okay. And dy dx is 1 minus y. Yeah, so, okay, yeah. That does fit the differential equation. And it does have 0, 100 in it. I can see that. All right, so this is 10. dy dx equals basically e to the negative y. I'm going to multiply that over onto this side, and I'll have e to the y dy equals dx. So that'll be an antiderivative for e to the y with respect to y is going to be e to the y. An antiderivative for 1 with respect to x is just x plus c. So I'll take the natural log of both sides. It's not going to be log of the absolute value of x plus c because I'm solving an equation for y that starts with e to the y, right? The log of the absolute value, that only comes in when I'm taking the derivative of 1 over u with respect to u. Okay, so y is equal to the natural log of x plus c. And then, I need to use my condition. X is 2, y is 0. 0, and 0 can equal a log. A log can equal 0 because a log is just an exponent. So a log can equal whatever you want. It's the thing that we put inside the log that can't be 0, can't be negative. So 0 is equal to the natural log of x was, which one am I working here? 10. X is 2. Okay. And maybe you know that the log of 1 is 0, and so you just know that c needs to equal -1. But maybe you don't, and you need to convince yourself of the fact that c is going to be -1. What you're going to do is we're going to take e to both sides power to get at the thing on the inside of the log. So that's telling me that e to the 0 equals e to the log of 2 plus c, which is 2 plus c. Okay, so this is 1 equaling 2 plus c. Subtract 2 from both sides, and you get c equals -1. So my particular solution to that equation is going to be y equals natural log of x minus 1. Okay, number 11. Ooh, I like this one. This one's a little obscure on the antiderivative, but it's only in terms of x, so it's like, okay, this is just an antiderivative I've got to know. And this, maybe I'll just copy down the problem first. Okay. So I'm going to just solve it by directly anti-differentiating. Hey, this is one that we have to know. Okay, it's getting to the point in the year where you just have to know that this is anti-differentiable and what this is the derivative of. Okay, it's the derivative of arctangent. It's not the derivative of natural log of the absolute value of 1 plus x squared. Because, well, if you do think that that's the antiderivative, I'm just going to tell you to take the derivative of natural log of the absolute value of 1 plus x squared. And maybe I will do that on a scrap of paper that I can then, quickly take away so that you're not looking at it and thinking it's right work. I was going to put a little disclaimer there, but I'm just going to do it. I'm going to say just on the side, the derivative with respect to x of log of 1 plus x squared is equal to 1 over 1 plus x squared times the derivative of 1 plus x squared for the chain rule. And this is clearly not the same as 1 over 1 plus x squared. Okay? And the absolute value, adding the absolute value there isn't going to save you from that 2x coming out for the chain rule. That's just not how that's going to work. Okay, so that's why we can't just take the log of the absolute value of x squared plus 1. We need to know what the antiderivative is. Okay. And, hold on just a second. All right, that'll work. And so this is arctangent of x plus c. And then the initial condition I was given was x is 1 and y is pi. Oh, okay. Yeah. I was like, oh, an initial condition, but no, I see where this is going. Pi equals arctangent of 1. Another thing that we need to be able to evaluate in this class, plus c. Okay. The thought is, where is tangent most obviously equal to positive 1? Now, arctangent takes its values over here. And tangent is equal to 1 where sine is equal to cosine, which happens to be at pi over 4. This is where you could look at it like that. That's where tangent equals 1. Okay. Or you could say, and pardon me, I meant to write over here. We're trying to solve the equation tangent theta equals 1. Okay, that's what we're looking to do. Or I could say tangent theta equals 1. That's at pi over 4. Okay. the most obvious place where tangent equals 1. There's another place back here where tangent is equal to 1, but that's not so obvious. That's how arc trig works. It's the most obvious place where tangent equals 1. Okay, so that's pi over 4. So, wait, I'm not done doing my computation. Pi equals pi over 4 plus c. So I've got the whole one here and a quarter of it there, so that means c is 3/4. Okay, so my particular solution is going to be y equals arc tangent of x, which is the same as inverse tangent of x. Okay, we can write it either way in this class. I'm going to write it both ways just to make sure you're aware of that. Plus 3 pi over 4. Okay, that was a pretty good one. Okay, here's another one that's going to come in with some arc trig considerations. Okay. 12. And, you know, on arc trig, is it going to be on the quiz? No. Is it going to be on the test? Probably not. But, you know, if you miss the test and you have to take it late, very good chance. On the semester exam, definitely eligible. Okay, so you can't just ignore the obscure derivatives just because you think you shouldn't be forced to memorize them. Okay, it's tough. It's just, that's the expectations of the course. Yeah, I've been getting a lot of kind of, I wouldn't say complaining, but like apprehension about obscure trig derivatives and antiderivatives. And what I'm telling you, if you're watching this video, you're going above and beyond. I'm going to ask you to continue going above and beyond and just memorize the things you're supposed to memorize for the course. It'll just make your life much easier. Just do it now. Okay, so dy dx is y over the square root of 1 minus x squared. Okay. I'm going to separate variables, so I'll have 1 over y dy. Oh, this one's going to be wild. 1 over the square root of 1 minus x squared dx. Okay. Anti-differentiate both sides. I'll have antiderivative for 1 over y is going to be log of the absolute value of y. An antiderivative for 1 over the square root of 1 minus x squared, that's inverse sine, that's arc sine. Plus c. Okay. Now I'm going to take e to both sides power. And absolute value of y equals ce to the arc sine of x. Okay. And y equals plus or minus ce to the arc sine of x. When x is 0, y is negative 2. So I've got negative 2 equaling negative c, so I'm deciding I'm going to just use that negative, ce to the arc sine of 0. Okay. Well, just like the last one, when I set out to find arc sine of 0, really what I'm looking for is the most obvious place where sine of theta equals 0. Sine is the y-coordinate, and the most obvious place is going to be right here at theta equals 0. Okay, so inverse sine of 0 is equal to 0. So now I have negative 2 equals negative ce to the 0. Okay, that means e equals 2, and therefore y equals negative 2e to the arc sine of x. I wonder what that curve looks like. I bet it's got a limited... I don't know. I'd be very interested to know what that looks like. Hold on. Okay, so I graphed it on Desmos just really out of curiosity, and it did have a very limited domain and range, basically because inverse sine has limited domain and range. And then the curve, I don't know if it does actually extend all the way up to the x-axis, and it's just kind of the limitations of the graphing software, but it looked like that. But it did certainly go through the point 0, negative 2, which is comforting to us because we were looking for a particular solution to that differential equation that happened to pass through the point 0, negative 2. And at the very least, at least this curve passes through the point that we were given. Okay, so the last one is number 13, which is, okay, it's got a little chain rule in it, I like that. dy dx equals y plus 4 multiplied by cosine of negative x. Okay, so divide both sides by y plus 4, multiply both sides by dx, and I'll get natural log of the absolute value of y plus 4 equals, okay, an antiderivative for cosine is sine, leave the inside the same. But if the inside is linear in the independent variable and it has a a slope that's not 1, we might have to divide by that slope. So I'm going to divide by that -1 to prepare for the chain rule, right? Because the derivative of sine of negative x is cosine of negative x times -1. But I want positive cosine of negative x when I take the derivative of this thing, so I prepare for that there. Okay, now I'm going to just start getting at that y, just like always, c e to the negative sine of negative x. Okay. Then y plus 4 is going to be plus or minus c e to the negative sine of negative x. And y equals -4 plus or minus e to the negative sine of negative x. Okay, the initial condition I was given was pi over 2 and 1. So y equals 1. 1 is -4 plus 5. So I'm going to be using the plus and the plus or minus. E to the negative sine of negative x was pi over 2. So negative sine of negative pi over 2. Why did I do that? Why did I not do pi or 2 pi or 3 pi, right? That would make more sense, because now I'm going to be taking e to the 1. And hold on, there's supposed to be a c in there. I don't know what happened to that c. Right? Otherwise, I'd have nothing to solve for, and this would not be true. 1 is not equal to -4 plus e to the negative sine of negative pi over 2. All right, so trig. Negative pi over 2 is down here, right? Positive pi over 2, negative pi over 2, I just go backwards. And the sine is the y-coordinate, so it's going to be -1. So -1. Okay, so it's e to the 1. 1 equals -4 plus c times e to the first power. So I'm going to add 4 to both sides. 5 equals c times e. Whoops. And I'm going to get c, that's barely visible at the very bottom of my page. 5e to the -1. Maybe I'll say it like that. Okay, I think this is maybe one where, yeah, I'd have been probably better off to... No, this is not one where I'd have been better off to plug in earlier. Nothing you can do. Okay, it's just bad initial condition gave you a bad solution. So my solution is going to be -4 plus 5e to the -1 e to the negative sine of negative x. Now, if you really wanted to, you could say that that's -4 plus 5e to the -1 minus the sine of negative x to write it as one exponential if you like. Same thing. This is no more correct than the first version. Okay? And that was a really good selection of practice problems, extra practice problems. I very well may come back with yet another set of separation of variables examples, because this is maybe of the whole year in AP Calculus, this is the type of thing that you need to practice a bunch of times. And the more you practice it, the better you get at it, the more confident you feel in it. And when the time comes that you're going to work one of these problems and it's going to be worth, a lot of, like a handful of multiple choice questions just for one problem, you'll be able to collect points at a high rate of success. All right, so thanks for watching.